Imagine for a second that you've just secured, like, your most valuable possessions inside this massive, heavy steel vault.
Right.
You pull the door shut, you spin the dial, and you hear those heavy bolts click into place. It is completely impenetrable. But then a cold chill runs down your spine because you realize you just locked the piece of paper with the vault's combination on the inside.
Oh, man, yeah. That is a terrifying realization.
Right. And in the world of server administration, if you sequence your bootloader and your full disk encryption in the wrong order, that is exactly what you've just done to your own operating system.
Exactly. And it happens a lot more often than you might think. People rush into securing a system without really understanding the underlying mechanics,
Yeah.
Because security at the disk level, it's not just some software feature you toggle on. I mean, it is a full-on architectural commitment.
Welcome to the deep dive. Today, we're tailoring this exploration specifically for you, the learner, who really wants to understand the why and the how just beneath the surface of the command line.
Yeah. We are wrapping up our journey into Linux file systems today.
Exactly. We're pulling from the second part of a really fascinating set of system administration notes. Now, in our previous deep dive, we looked at the physical geometry of hard drives. So, platters, tracks, using tools to carve out physical partition boundaries. But today is entirely about defense.
Right. We're leaving the raw construction behind and looking at what it actually takes to secure those boundaries at the block level, which is really the logical next phase.
Makes sense.
I mean, establishing a partition just tells the OS where data is allowed to sit.
Right. It's just the boundary.
Exactly. But without an encryption layer, any data sitting in that partition is vulnerable to anyone who can just get physical access to the drive.
Yeah.
You can have the strictest user permissions, the best firewalls.
But if someone just physically pulls the drive out of the rack and plugs it into another machine?
Game over.
Yeah.
Pretty much.
Yeah.
Those software level permissions mean absolutely nothing at that point. The data is just sitting there in plain text waiting to be read.
Okay, let's unpack this. I want to build a mental model for what we're actually doing here. So, if the partitioning process we talked about previously, like using a tool like FUDDisk, is akin to building the concrete walls of a massive warehouse of safety deposit boxes,
Sure.
then the encryption we're discussing today isn't just, slapping a padlock on the front door. We are scrambling the locks on every single safety deposit box inside that warehouse.
That gets us halfway there. But the digital reality is actually a bit more rigorous than a physical warehouse. We aren't just scrambling the locks. We are fundamentally scrambling the dimensions, the material, the contents of the boxes themselves until the correct key is applied. And the syllabus actually schedules this encryption step right alongside formatting and mounting.
Because it's foundational, not an afterthought.
Exactly. And the notes highlight a very specific, highly standardized tool for achieving this on Linux, which is LUKS. That stands for Linux Unified Key Setup.
And LUKS is really the heavy hitter here. The documentation makes it clear that while there are a bunch of ways to encrypt data, LUKS has become the industry standard for full disk or partition encryption.
Standardization is definitely the operative word there, because before LUKS, different Linux distributions might use completely different, totally proprietary methods to handle block-level encryption.
Oh, wow. That sounds like a nightmare.
It was. If you encrypted a drive on one system, you might not be able to unlock it on another, even if you have the right password. So LUKS provides this universal format. It operates at the block device abstraction layer.
Okay, so what does that actually mean in practice?
It means it intercepts the raw ones and zeros before they are ever written to the physical disk sectors, and it encrypts them.
But here is where it gets really interesting. I think this is a critical friction point. The notes explicitly state that LUKS is used for full disk or full partition encryption.
Yeah.
So if I am encrypting the entire partition, and let's say that partition contains my Linux operating system, my kernel, all my system files, how does the server even turn on?
That is the big question.
Right. Doesn't the computer need to be able to read the operating system off the disk just to boot up and prompt me for the LUKS password? I mean, This feels like an impossible chicken and egg scenario.
It is one of the most common conceptual hurdles in system administration. Because, how do you unlock the vault if the tools you need to unlock it are literally locked inside the vault?
Exactly.
The answer lies in how a modern Linux system actually sequences its boot process. The documentation notes that LUKS is designed to be easily integrated into boot processes. But to understand how, we have to look at what happens the exact millisecond a server receives power.
Walk us through that sequence, because clearly the motherboard isn't decrypting the drive.
No. The motherboard's firmware, like the UEFI or BIOS, knows absolutely nothing about LUKS. When the server powered on, the firmware looks for a tiny, unencrypted piece of software called the bootloader, something like GRUB. And this bootloader has to live on a small, separate, unencrypted partition.
Ah, so there is a small part of the drive that's just left in the clear.
It is an absolute requirement. The bootloader's only job is to load the Linux kernel and an initial RAM disk, which is called the initramps, into the computer's memory.
The initramps. Okay.
Yeah, this initial RAM disk is basically a miniature temporary operating system that runs entirely in the server's RAM. It contains just enough drivers and just enough basic logic to understand what a LUKS partition even is.
So it can display the password prompt?
Exactly. It throws that prompt on the screen and waits for the administrator to type in the passphrase.
So the system wakes up, boots into this temporary unencrypted waiting room, asks for the password, and once you provide it, it unlocks the massive encrypted partition, throws away the waiting room, and boots the real OS.
That is the mechanism. But we actually need to dig one layer deeper into how that password unlocks the data, because the mechanics here are fascinating. When you type your passphrase into that prompt, you are not actually decrypting your terabytes of data with that specific password.
Wait, really? Then what is my password doing?
It is decrypting the LUKS header. See, every LUKS encrypted partition has a small header section at the very beginning of the partition. And inside this header, LUKS stores a randomly generated, incredibly complex cryptographic key.
The master key.
Exactly, the master key. It is this master key that is used to actually encrypt and decrypt the billions of blocks of data on the drive. Your passphrase simply unlocks a key slot in the header, which then releases the master key to the system.
Oh, that is brilliant. I see the utility in that instantly. Because, I mean, if the password I typed actually encrypted the underlying data and I wanted to change my password,
The server would have to spend hours.
or maybe even days, re-encrypting every single byte of data on a massive 10 terabyte drive.
Exactly. And furthermore, it allows for multiple users, because LUKS supports multiple key slots.
Oh, so you could have different passwords for different people.
Right. You can have the system administrator's password in slot 1, a backup recovery key in slot 2, maybe an automated network unlock key in slot 3, and any of them can unlock the header to access that single master key.
So if an admin leaves the company, you don't have to re-encrypt the whole server.
You just delete their specific key slot from the LUKS header. The master key remains entirely unchanged, and the data is perfectly intact.
That distinction between the passphrase and the master key is a massive aha moment. Okay, so we understand what LUKS is, we understand the bootloader sequence, and we get the header. But I want to pivot to how an admin actually deploys this, because the course notes outline a very specific, rigid process.
They do?
They mandate that you must start with an empty partition using the fdisk command. And I have to push back here on behalf of the listener. Let's say I have a 2 terabyte external drive, completely full of historical server logs. You're telling me I cannot just run a command to encrypt those files in place. I have to move 2 terabytes of data off the drive, set up LUKS, and then move 2 terabytes back. Why can't Linux just encrypt it on the fly, like putting a password on a zip folder?
That is a massive pain point for anyone setting up secure storage for the first time.
Mm-hmm.
Why the need for a blank slate?
Right.
Well, if we connect this to the bigger picture, the answer requires understanding the fundamental difference between file-level encryption and block-level encryption.
Okay, break that down for us.
Well, a password-protected zip folder operates at the file level. The operating system still sees the drive, it sees the directories, it sees the zip file itself. But LUKS, as we established, operates at the block level. It sits underneath the file system.
So LUKS doesn't know what a file is. It doesn't know what a directory is. It just sees physical sectors on a spinning disk or memory cells on an SSD.
Right. To LUKS, a photograph, a text document, and a kernel module all look exactly the same. They are just a stream of ones and zeros. So let's look at the sequence, the notes demand. Step 1, you use fdisk to draw the raw physical boundaries of the partition. This creates an empty container.
Just the walls.
Just the walls. Step 2, apply LUKS to that empty partition. Step 3, use the mkfs command, which is make file system, to create the actual directory structures like the ext4, xfs file system inside the encrypted volume.
Which is where things like superblocks and inodes come in.
Let's expand on that. When you run mkfs, the operating system writes critical metadata to the drive. It creates inodes, which are basically index cards telling the system exactly which physical blocks belong to which files. It creates a journal to track ongoing changes. It builds the entire map of how data is organized.
So if I try to apply LUKS to my 2 terabyte drive of server logs that already has a file system on it,
You will cause catastrophic data loss.
total destruction.
Yeah, pretty much. Because if you apply block-level encryption over an existing file system, LUKS will systematically scramble the ones and zeros of the underlying blocks. The operating system's virtual file system layer will look at the drive, try to read the superblock to understand the layout, and it will just see encrypted gibberish.
It won't be able to find the inouts.
Exactly. You won't know where any files start or end. By encrypting the foundational blocks out of sequence, you effectively shred the map that makes the data readable in the first place.
That makes the rigidity of the sequence completely understandable. I mean, you build the property lines with fdisk, you build the encrypted vault with LUKS, and only then do you run MKFS to build the organizational shelves inside the vault.
Yes.
If you build the shelves first and then try to build the vault through them, you literally crush the shelves.
Sequence is everything here. And this brings us to what happens after the file system is built. Because the data doesn't just magically appear. The administrator has to explicitly mount this encrypted volume to make it accessible to the users or the network.
Right, mounting. Now, we've talked about mounting standard partitions before. You just point a directory, like /mint/data, to a partition, like /dev/sdb1.
Right.
But with LUKS, there is a middleman involved.
A very vital middleman, because the raw partition /dev/sdb1 is entirely encrypted. If you try to mount it directly, the operating system will just throw an error because it cannot read the file system. Instead, the admin uses a command to open the LUKS partition and provide the passphrase.
Decrypting the master key from the header.
Exactly. Once the master key is unlocked, the Linux device mapper subsystem steps in. It creates a new virtual block device, typically located in the /dev/mapper directory. And this virtual device acts as a transparent translation layer.
So when I save a file, I am actually saving it to this virtual /dev/mapper device. The operating system thinks it's writing to a normal unencrypted hard drive.
Yes.
But as the data passes through that virtual device, LUKS intercepts it, encrypts it on the fly using the master key, and writes the scrambled data to the actual physical disk.
And the exact reverse happens when reading. The OS asks the virtual device for a file, LUKS, pulls the encrypted blocks from the physical disk, decrypts them in the server's CPU, and hands the plaintext file to the operating system. And it happens in milliseconds.
That's incredibly fast.
It is. In fact, modern processors have specialized hardware instruction sets, like AES-NI, specifically designed to handle this cryptographic math incredibly fast. So the performance overhead of full disk encryption is often negligible.
So what does this all mean for you? The learner listening to this right now. Why does this specific architecture, the bootloader handoff, the LUKS header, the strict fdisk, LUKS, MKSS sequence, the virtual mapper, why does this matter beyond just passing a system administration certification?
That's a great question.
In the background material for this course, there is a mention of an upcoming server deployment night. It's this massive lab where students have to set up a server acting as a secure firewall and router. And the syllabus specifically notes that things like pizza and soda are integral to the design process.
Which is highly accurate, by the way.
Right. It sounds like a joke, but it highlights a really profound truth about system administration.
It highlights the necessity of deliberate, focused engineering. You have to have an open mind and really focused thinking.
You cannot just show up, start typing commands, and hope for the best. You are designing a secure environment from the ground up. If you mix up the steps, if you format the file system before you apply the encryption layer, or if you forget to configure the unencrypted boot partition,
your server will not boot, your data will be corrupted, and you will be starting over from scratch. Understanding the block-level abstraction gives you a mental map. It allows you to visualize exactly where the data is in plain text and where it becomes ciphertext.
It forces you to transition from thinking like a user who just clicks save to thinking like an architect.
Precisely. You begin to see the storage stack not as a single hard drive, but as a series of interconnected layers. The physical sector, the partition boundary, the cryptographic layer, the virtual mapper device, and finally, the file system. When a system fails to mount a drive, or a server just hangs on boot, an architect who understands these layers knows exactly which logs to check and which subsystem is failing.
It fundamentally upgrades how you interact with technology. Let's take a quick moment to recap this journey. We started by moving beyond the physical geometry of hard drives and recognizing the absolute necessity of block-level security.
Right.
We explored LUKS, understanding how its standardized approach and really clever use of master keys hidden inside headers allow it to secure massive amounts of data efficiently.
And we solved the boot paradox.
Yes. Seeing how a tiny, unencrypted bootloader and an initial RAM disk act as the foyer to our vault. And most importantly, we broke down the rigid sequential necessity of starting with an empty partition, using fdisk to draw the lines, LUKS to build the vault, and only then using MKS to create the file system, avoiding the catastrophic destruction of our own metadata.
It is a rigorous, unforgiving process, but in modern server administration, it really is the only viable path to ensuring that data remains intact and fundamentally secure from physical compromise.
It is a phenomenal system. But as we close out this deep dive into file system operations, I'm going to hand it over to you because there's one final, incredibly high-stakes implication of this architecture that we need to address. We've built the perfect defense, but perfect defenses come with their own unique kind of danger.
They do. The danger of succeeding too well. We've spent this time discussing how to build an impenetrable digital vault, ensuring that without the passphrase, the master key remains locked and the data remains an ocean of cryptographic noise.
Yeah.
The math behind LUKS is virtually ungrokkable by brute force. But consider the reality of the architecture we just explored. The master key is stored in the LUKS header at the very beginning of the physical disk. What happens if a power surge, a failing hard drive sector, or just a careless administrative command overwrites just the first few megabytes of that partition?
Oh, wow.
The data is still there, perfectly intact on the rest of the drive, but the header is corrupted. The master key is gone. In the relentless pursuit of ultimate security, an administrator must constantly weigh a terrifying paradox.
It is.
Making data completely inaccessible to bad actors operates on the exact same mathematical mechanism as locking yourself out of your own server forever. It is a razor-thin line between a secure vault and a digital black hole. Something to consider the next time you provision a drive.
That is a terrifying thought to leave on, but a necessary one. Until next time.